Assalamualaikum and a very good morning everyone. This is the first lesson for this week, week 5. And in this topic today, we're going to revise some of the topic that you've already learned from your previous subject, mechanics of solid. So today we're going to look into mechanical properties of materials, specifically just on metals. So by the end of today's lesson, you should be able to describe engineering stress and engineering strain. You should be able to give a given engineering stress and strain diagram. You should be able to determine the mechanical properties of metals. And also you should be able to name two most common hardness testing techniques and give the difference between them. Many materials, when in service, are subjected to forces and load. So you have already learned this in mechanics of solid. So when being applied, a load being applied to the materials, we will impose stress and strain to the materials. So we must know the characteristic of the material and to design the loaded member using materials that will not deform excessively and fail. So for structural member, we're normally going to keep them working just between the elastic region. So we don't want our member to start, when load being applied, to start deform plastically. So we must know the characteristic of the materials in order for us to understand this. So the mechanical behavior of the material is the relationship between its deformation to an applied load or force. So in this topic today, we're going to look into how can we determine the material, the mechanical properties of the materials using tensile tests. All right, so if you can still remember from mechanics of solid, stress and strain are the fundamental concept that I use to describe how material respond to external force. But what is stress and strain? So let me first begin with stress. So if, let's say, I have this structural member here, and say I apply a downward force on the surface area of this structural member. This force is trying to compress the beam from the top. So due to this beam will experience some sort of stress. The member is in uncomfortable state. So the atom inside this member, inside these materials, is a little bit too close than what they want to be. So this will result in intermolecular forces or interatomic forces. And if the applied force is within the elastic limit, and if I remove that applied force, these intermolecular forces or the interatomic forces will bring back the structural member to its initial states. So this is a simple explanation of stress. Mathematically, we calculate stress using this equation. So stress is equals to force, the internal force divided by the surface area of the member. So there are two types of stress. One is normal stress and we have shear stress. And for normal stress, it can be compression and also it can be tension stress. So in the nutshell, stress is an internal state that develops within a body as it responds to externally applied load. So take example of this beam here, and if I load them actually to elongate them. So what's going to happen is that when I apply the load, uniaxial load at the axis, longitudinal axis of this beam, it is going to elongate. So the internal force will develop to resist this applied force because of the atomic bonding. That materials, the atoms, is now being stretched. The bonding between the atoms is now being stretched. But they would resist that stretch and they will develop the internal force to resist that stretching of the bonding. So if I do method of section and I expose these internal forces, the effect of the internal forces for this member to be in equilibrium must be equal to the effect of the external forces. So the stress is actually the intensity of this internal force along that surface area of the beam. So the equation for stress is force divided by area. And this is represented with the Greek letter sigma. So for normal stress, it is when the applied force acting on the normal of the cross-sectional area. So to explain shear stress, I will use this book here as our material. So let's say this is our structural member. So this member has a very good tensile properties. So when I stretch them, they did not stretch. When I try to expand them this way, they're not expanding. And also when I try to compress them, they're not deforming. But as soon as I applied force parallel to the surface, you can see that this book starts to deform. So this stress that is generated from this applied force is what we call as shear stress. So now that you understand how the materials, the atoms is arranging themselves in the material. So let's say I have this body of a single crystal materials, and you know that these materials have atoms stacked one on top of each other. So it's going to be looking like this book. So there's a layer and layer and layer of atoms arranging themselves. And if I applied force to this surface here, what is going to happen is that this is the original, and then it's going to move like this. All right? But why doesn't it keep moving? So if we look at just a two layer here, just look at the two layer here, one on top of the other. And when we applied force, this layer here will move relative to the other one. So it's going to move. But because of the atomic bonding, internal force will be developed to resist that external force. So the interatomic bonding will try to bring them back to its initial states. So if, let's say, I remove this force, it will, if it's still in its elastic region, it will move back. So this force here, if we look at our beam, the one that we saw just then for normal stress, if the body is not loaded along its longitudinal axis, instead it's loaded perpendicular to its axis, so it is parallel, the force is parallel to the cross-sectional area of this beam, what will be developed is what we call as shear stress. And shear stress is represented by the Greek letter tau, and it is equal to the force divided by the cross-sectional area. Now let's look into strain. So strain is defined as the change in dimension of a material based on its original dimension as a result of an applied stress. If we have the same beam here and we applied compression load here, it will deform this beam, and strain is defined as this change in length here divided by its original length. So that is strain. So why do we need to specify strain instead of just specify the change in elongation? So a body that if it's deformed and we measure the dimension of the deformed body, this is a very geometric dependent quantity. So we want to get away from it. If let's say I have this material here and I applied a force P here and it's elongated by delta L. The same materials with the length of 2L, if I applied force F here, it's deformed by 2 delta L. But every time I have to specify the actual length. So we don't want to have to specify the actual length. So let's say I said a strain of 4% of steel specimen means that in principle it has a lower ductility than elongation of 10% of wooden specimen. So regardless of its respective actual length, I can just tell you that the strain is 4% for steel and for 10% of the wood specimen. And by just saying that, you know that the steel has a lower ductility compared to the wood. So normal strain can also be divided to two. So we have tensile strain. When the materials is being elongated, we call them tensile strain, and that's going to be positive value. And when that member is going to be compressed, we're going to call them as a compressive strain, and this is going to be a negative value. And as for the shear strain, it is measured as the displacement of the surface that is in the direct contact with the applied shear stress to its original position. And the equation for shear strain is equals to this equation here. And tangent theta here of this angle is equals to delta L divided by L. So this is for shear strain. So the main topic today is that we are going to look into tensile test, tension and compression test, and we're going to look how stress and strain is related through this test. So today we will discuss the test and how the diagram is plotted. So the strength of common engineering materials such as metal, ceramic, polymer, and composite can only be determined by experiment. And this experiment is what we call as tensile test. So the tensile test can also be used to determine the fracture strain in order to obtain the information about the toughness of the materials and also the ductility of the materials. So strength of materials is the ability of the material to sustain load without deformation. So in order for us to obtain these mechanical properties of the materials, we must conduct tensile tests. When you come back to UTM, you will be able to see the demonstration on how this test will conduct. And today we're just going to see and to look at it virtually. All right. So the tensile test, the sample of the tensile test for each materials will be standardized, and therefore we can compare them. So the standardization of the geometry is intended to achieve comparability of the material parameter that we obtain. So this is the standard dog bone. We call this as a dog bone specimen. And for metal, we normally have it shaped this way before we can conduct the experiment. All right, so the first thing that you need to do when you have this specimen is to punch these two holes here, these two holes, and this is going to be the initial length for this specimen. So you need to from the experiment, we will calculate the strain of this specimen after it's being tested. So before the start, the initial length will need to be specified, and also the initial cross-sectional area. So the example metal specimen normally will have this dimension. 13 millimeter diameter, and the initial length is 50 millimeter. So the machine is used to stretch this sample very slow at very constant until it will fail. So this is the schematic of the machine. that is used to stretch these materials. And this machine is designed to read the load required to maintain the uniform stretching. So bear in mind that the reading that come from this tensile test always going to be force versus the displacement. So at frequent interval, the data is going to be recorded of the applied load. The elongation between the punch mark on the specimen is measured using either the caliper or an extensiometer. And this value is going to be used to calculate the normal strain. So here I have a video of how tensile tests being conducted, and I would like to share it with you. The force and displacement data that we obtain from the tensile test can now be converted to stress and strain curve. We have calculated the initial length when we also have calculated the initial cross-sectional area, and from there we can convert it and we can plot stress and strain curve. So a stress and strain diagram is obtained by plotting the various value of stress and corresponding strain in the specimen. So in contrast to force and elongation curve, pure material parameters can be determined from stress strain curve, which are no longer dependent on the geometry of the specimen. So if let's say we plot force versus elongation, so this diagram here does not allow us to have any statement be made about the strength of the material, because what you have plotted here is geometry dependent. If let's say I have the green color specimen here, which is wood, and I have the blue color specimen here is steel. And according to my force elongation curve, I would say that the wood can sustain a higher load if we compare with steel. But this is not true. If we have these two materials, these two specimens are not standardized, one thing. And another thing, we know for certain that steel has a higher strength than wood. So if we compare this straight away from the force elongation curve, whatever we come up with is not the statement that will tell us the strength of these materials. So to eliminate the influence of specimen's geometry, the force is related to the initial cross-sectional area and the elongation to the initial length. So we plot instead the stress and strain. And using this way, the purely material dependent, geometry independent curve can be obtained. So if the corresponding value of stress and strain are plotted so that the vertical axis is the stress and the horizontal axis is the strain, the resulting curve is what we call as the conventional stress-strain diagram. So conventional stress-strain diagram is when the normal stress at any point in the diagram is always related to the original cross-sectional area of the materials, and the normal strain is always related to the original length of the specimen. And this is what we call as conventional stress-strain curve or engineering stress-strain curve. So the two stress-strain curve diagram for any particular material will be quite similar, but they will never be exactly the same. So this is because the result actually depends on the variables such as material composition, the microscopic imperfection. So there are no two specimens that can be exactly the same in terms of their microscopic imperfection and also the way it is being processed. So temperature can also affect the tensile result of the tensile test. So this is an example of engineering stress versus strain curve of mild steel. So this steel has been used a lot as a structural member. And from this stress strain curve, you can see there are four distinct regions under the curve of the tensile of the stress strain curve. So we have elastic region. So in this region here, the material behave elastically. And as soon as elastic limit is reached, the material is going to yield. And after that, there will be a region that we call as strain hardening. So in this region, the material is actually getting stronger, because as you can remember from the previous lecture, that what happened here is that we introduce a lot more dislocation. So the dislocation starts to going to entangle with each other, and you need a higher load to actually move them. And after a certain stress, which is the ultimate stress, this materials is going to start to fail, and it is going to start to form what we call as non-uniform plastic deformation. So that is what you see from the video, where the material starts to form necking, and after that, if you apply more load, this material is going to fail. So the elastic behavior, the region of the elastic behavior, in this region, a linear increase in which the strain increases in proportion to the applied stress. So on this straight line only, an elastic deformation takes place. So what happened here if you release or if you unload the materials, it will go back to its initial condition. But if the force keep going to be applied and it's going to be increased, it will start to deform plastically. So the deformation of the specimen will disappear completely after the force has been removed. So a slight increase in stress above the elastic limit will result in breakdown of the material, and it will cause it to permanently deform. So this stress that causes yielding is what we call as yield stress. So this is the point where the material will deform plastically, and even after you remove the load, this material cannot go back to its original it's to initial states. So this is where plastic deformation happens. So after yielding, we can observe a region as the region that we call as strain hardening. So in this region, the stress must be increased again for a further elongation because of the entanglement of the dislocation that being introduced to the materials. So until it reaches a maximum stress that we refer to as ultimate stress. So the cross-sectional area of the specimen decreases uniformly over the entire region of the strain hardening. So you cannot see the necking happening yet. And eventually, after it reaches the ultimate stress, the cross-sectional area will begin to decrease in a localized region. And as a result, necking will be formed in this region as the specimen elongates further. And the specimen will finally break, and the stress where the specimen breaks is what we call as fracture stress. So during necking, the plastic deformation is not uniform. So at this point, the specimen only elongates within the necking zone until it finally breaks. So materials that can be subjected to large strain before it fractures is called as a ductile materials. So ductile materials are capable of absorbing shock or energy better than the brittle materials. So metal usually exhibit, if we compare to ceramic materials, metal is considered as ductile materials. So if they become overloaded, they will usually exhibit large deformation before failing. So you can see that within that necking region, the plastic deformation is severe. If we compare to brittle materials, it will have only a flat surface. We will talk more about the failure, how materials fail, in our next module, our next lesson. So ductility of any materials can be calculated using the sample of the tensile test. So when we loaded that materials and we fracture them, the ductility of the materials can be calculated using this equation here. So it is basically the strain of the materials when it failed. So what we need to do is we need to measure the distance of the punch hole that we initially have, and we measure it again after it is being fractured. And then we use this equation here to calculate the percent of elongation at fracture. And that is the ductility of the materials. So material like mild steel has a typical value of ductility of 60%. So if we go back to the stress strain curve of mild steel, we can see there are 4 distinct regions here. And we can see that there's a region of constant yielding here. So this kind of characteristic of stress strain curve also exhibit, you can also see this in brass and molybdenum and also zinc. However, not all metal will have this characteristic of stress strain curve. In most metal, constant yielding will not occur beyond the elastic range. So in some materials, the stress at which the material change from elastic to plastic is not going to be easily detected. So for example, materials like aluminum, the stress strain curve will look totally different. So in this case, we have to use offset method to determine the yield strength. So the stress strain curve of aluminum will look like this. So from here, you cannot tell exactly where is this material is going to yield. When is the plastic deformation is going to happen? So we need this information in order for us to use this material in any application. So we don't want them to reach that yield point where the materials is going to deform plastically. So we need to establish where exactly the yield point. So what you can do is using the offset method. So the first thing is we define a point. So here I label them as point A, which correspond to the 0.2% of the original gauge length. And I will draw the line AB equal to the slope of the line of this linear path here, and the intercept of this line with the stress strain curve is what we call as the offset yield strength. So the yield strength of that materials is there. So now using stress strain curve, you can define the yield strength of these materials. Material that exhibit little or no yielding before failure is what we refer to as brittle materials. So the fracture surface of the materials will look like this, where it's almost a flat surface there. So an example of gray cast iron, example of brittle materials is gray cast iron. And these materials, the stress strain curve will look different again. So with brittle materials, the stress strain curve characteristic will look totally different. So for gray cast iron, the stress strain curve when it's loaded in tension will look like this. So just focus your attention to the one in the square here. So these materials, when we load it in tension, it will not have a well-defined yield point. And also you cannot see any strain hardening region. So once it's reached its ultimate strength, it will break straight away. So this is the characteristic of brittle material, stress strain curve of brittle materials. What happened here is because for gray cast iron, there's a lot of volume defect. So we have a lot of micro cracks and also a lot of porosity. And also we have inside this microstructure, we have what we call as flakes. And this flakes has a very sharp corner. So the corner here is where the stress concentrated. And when we applied load, axial load, a tension load, what will happen, this all volume defect is going to interact with each other and they are going to propagate straight away. So this is why the fracture surface of these materials is going to be flat. So the crack is going to propagate rapidly under tension load. However, when these materials is being compressed instead, so this is the characteristic of the stress strain curve when it is being loaded in compression. So what happened when we load them in compression? These cracks inside these materials or even the porosity, when we compress them, it is going to close. And these materials is going to bulge. So that's why they are very good in compression. So materials such as gray cast iron exhibit a much higher resistance to axial compression. And when they're being loaded in compression, the specimen will end up looking like this. So to compare the stress strain curve behavior of brittle materials and ductile materials, you can see that for ductile materials, there are no region where this materials is going to be strain hardened. The plastic deformation of brittle materials is almost non-existent, and for ductile materials, it will undergo a large plastic deformation before it failed. Another material properties that you can obtain from stress strain curve is the Young's modulus. So the Young's modulus is the modulus of elasticity of a material. It represents the factor of proportionality in Hooke's law, which relates the stress and the strain. So from the stress strain curve, the slope of the linear region is the Young's modulus. So if you calculate that slope, you will get these intrinsic properties of the materials. So modulus of elasticity is the mechanical properties of materials that indicate the stiffness of the materials. So for example here, most grade of steel have the same modulus of elasticity, which is 200 gigapascal. So no matter how many times you shape these materials or you perform forming process to these materials, this modulus of elasticity of the material will not change. It is the intrinsic properties of that particular materials. The modulus of elasticity can be used only if the material has a linear elastic behavior, and beyond this linearity limit, the relationship between the stress and the strain is no longer linear. So the equation of Hooke's law is no longer valid. So another properties that we can obtain using the stress strain curve is the modulus of resilience. So resilience is the ability of the material to absorb energy when it is being deformed elastically. So modulus of resilience is defined as the maximum energy that can be absorbed per unit volume without creating any plastic deformation. So you can calculate modulus of resilience by calculating this area that I shade as red color here. So this is the area of this triangle here, which is equal to this one. And using Hooke's law, we can relate that with the Young's modulus. So this one is equals to stress divided by the Young's modulus. So you will get this equation here to calculate the modulus of resilience. Another properties that we can define using stress strain curve is the modulus of toughness. So this is the amount of strain energy per unit volume that a material can absorb before it fractures. So to calculate the modulus of toughness is to calculate the area under this curve here. So materials that exhibit large area under stress strain curve means that it has higher toughness. So it can absorb more energy before it fractures. So normally materials that is ductile will have a large area under its stress strain curve, and materials that is brittle will only have can only absorb little energy before it starts to fracture. So using the stress and strain curve, you can see that it can provide us with a lot of information about the materials. So from the stress strain curve, we can define the yield strength, we can define the ultimate strength, and we can also define the fracture strength of the materials. On top of that, we can also define the modulus of elasticity of these materials, and we can define its modulus of resilience and also the modulus of toughness, or how much energy it can absorb before it starts to fracture. So just by doing one testing, we can gather a lot of information about these materials. So you can see how important is tensile testing to engineering materials. So I'll end this discussion here today. I'll finish up with the rest of the slide together with failure of materials in the next lesson. So before I end up this lecture, I would like you to finish up with this example, solve this example, and I would like you to share your answer to the rest of the group in the group WhatsApp. And it doesn't matter if it's right or wrong, just share it together so we can learn together. And at 9 o'clock, I would like you to log into WebEx, and we can discuss this question together, and we will discuss about the questions that I gave you in quizzes as well. All right, so I'll see you at 9 o'clock through WebEx. I'll see you soon. Thank you.